Hello, it's Keith here, and this is lesson 1 of my PowerPC assembly programming tutorials, a new tutorial series. So we're going to be learning how to use the PowerPC, how to program it, and we're going to be doing so on the GameCube. I've got a GameCube emulator we're going to be compiling our examples to. Now, if you're new to my tutorials, I need to point some things out. Well, basically, the first thing is all of my tutorials, you can go to my website. You can download the source codes and the build scripts and you can compile them yourself. So on my website, there are two files. There is a sources file, which is the latest version of the source code. And there is a DevTools file, which includes the Notepad editor that I'm using, the scripts that I use to assemble, the assemblers, and the emulator. So hopefully you can download all of this and you can try it out at home. Because while we'll be going through all of the examples and I'll be discussing how they work, firstly, you will learn better if you are actually trying them out yourself. And secondly, I'm hoping you'll actually start to maybe developing a few little things of your own, and so you can use my my tools as a starting point, either just using the assemblers or using the emulator, whatever helps you. So go to the website and download those. The other thing I would strongly suggest you will want to go and download is my free cheat sheet. There's a printed copy I've got here. You can download this as a PDF and you can print it out. It covers the PowerPC as well as every other assembly language that I've covered in my tutorials, which is all of the major ones basically. Now the final thing I do have to do is I have to shell my book, because based on my view counts I'm never going to fund my programming from my YouTube views, and so I've got a couple of books for sale. They cover 10 assembly languages in total, 5 in each of the 2. They don't cover PowerPC yet, but if you're watching this in 2024, I'm hoping to have a new book out by then, volume 3, which will cover PowerPC, so please take a look out for that. Anyway, enough shelling, let's get on with discussing the PowerPC. First of all, what we're going to have to discuss is a few bits of theory for the PowerPC, because there's a few gotchas that you might need to bear in mind if you are familiar with other systems. And the first of these is the official IBM documentation's rather weird definitions of bit numbers. Now, everyone in the entire world decided that the least significant bit, the bit with a value of 1, was bit 0. The bit with a value of 2, the next least significant, would be bit 1, and so on. So the most significant bit would be bit 31. Everyone has agreed on this. So the Z80 agreed on this, the 68000 agreed on this, the 6502 agreed on this, even the 8086 seemed to think that was a good idea. IBM, however, said no, we will not do that. We will do the complete opposite. The most significant bit is numbered as bit 0, and the least significant bit is bit 31. I was hoping I might be able to avoid doing this and I might be able to just use the regular versions, but not only does that make reading the documentation impossible, it makes coding the processor impossible, because some of the processor commands use the bit numbers as their operands, and that won't work if you're using other bit numbering formats. So what I've basically got is whenever I'm having to refer to bit numbers, you will see that I have two rows. One is marked as IBM bits with the IBM numbers of bits, and the other one is in grey, and that is marked as bits, and that is the bit numbers as any other processor would identify them. Now, this rather obscure bit numbering is an IBM thing. The IBM 360 and 370, which I'm also planning on covering later on, they also use these IBM numbering. So it's just no one else ever, to my knowledge, has done. So it's a bit annoying, but we're going to have to live with it. Now, one of the other things that it is also a bit of an IBM thing is the register numbers and their purposes, and this is something that is in some places not very well documented. Now, the first thing is R0. R0 is our first register. We have a total of 31, so R0 is our first register, but it doesn't actually always work the same as the other registers. Some commands use this as a hardwired 0, and so when you try and use R0 as a source, it will actually contain the value 0 even if R0 has the value 5, for example. This is quite clever because it makes the commands like add be able to work as a load command. So from a design point of view, it's very smart, but as a user point of view, it's a little bit confusing. Basically, the simple thing is ignore R0 unless you're sure what you're doing. Start from R3 as your first register. The other reason for that is R1. Very poorly documented, but R1 is generally accepted to be the stack pointer. I say poorly documented because the processor documentation never mentions this fact, but all of the other documentation will assume that it is stack pointer. So very confusing there. I think that the documentation, the official processor documentation, should have said the standard is for I1 to be the stack pointer, but it doesn't do that. So R1 also has the alias SP for stack pointer. R2 is often considered to be a table of contents pointer. Doesn't really mean a whole lot. It's a lot less strict, but as I say, for practical purposes, just consider R3 to be your first register, and everything up to R31 to be free for your use, and that'll get you going just fine. You won't have any problems. We've got some more documentation on the website here, which you can read at your leisure or not, because we will come to all of that later on in our actual programming. Well, I've now been gibbering for 5 minutes, and one person in my ARM tutorials complained that was far too long. So let's get over and let's actually see some code running. Okay, so we're going to fire up here. This is the example, minimal.asm. If I press F6 on my keyboard, the way this Notepad++ is configured, it will run an execution command. But basically, this is just firing up a batch file, assemble elf.bat, and specifying the file name and the current directory. This is the script I'm working with. There is an alternate one, eabi-dol, but that is not appropriate for this file. That needs to build the entire file that the GameCube emulator requires. So if I just run this now, this minimal example will assemble. And what do we have? Well, we have a register shown to the screen with its value. That is because of this show hex function. We have this hello world message here, a nice hello world. That's because of this print string function. And then we have a dump of all the major registers here because of this monitor. And then finally, even more than that, we've got a dump of some of the memory here. And that's because of this memdump function. Okay, well, awful lot of stuff's gone on there. Well, how does this work? Well, there's an awful lot of code doing the background work for this. We've initialized the screen, the hardware. We've shown those various things to the screen. There's routines to do that. There's a font. There's bitmap drawing routines. All of that is being hidden from us, and that is the purpose of this minimal example. What I'm intending you do, you see, is you can use this as a template for your learning. Basically, just replace this part here, all of this highlighted bit here, with whatever you want to test. Use these functions if they help you. If you don't, just ignore them. All you need to do then is include command here with the dot at the start. This is specifying an additional file to attach to our source code. So we're including basic header here, and we're including basic footer here. And those are doing a lot of the work for us. Now, let's just briefly look at what else we've got on the screen here so that we can understand what a basic assembly file will look like on the PowerPC with the assembler that I'm using. Now, the first thing to notice that's rather annoying for me is that the comments start with a hash and not a semicolon. So you will see here in all of these cases, I've actually put a hash and a semicolon. You don't need to for the assembler. The semicolon is simply so that the coloring matches, because the Notepad++ I'm using expects a semicolon in assembly to be a comment, and so just for convenience to match the coloring, I'm putting a semicolon, but you don't need to. It's the hash that's doing all the work there. So that's just something important to notice. We then got various other commands here. We're going to go all over these in the following tutorial series, but basically a command is always indented by a tab like this. You can see here's a command lis here, that is the command, and then it's got two parameters. The R3 here is the destination on the left. The other parameter on the right of the comma here is the source. So the source is usually on the right, the destination is usually on the left, and what those two have done to them depends on the command here, and we're going to look at all of those separately, so I'm not going to discuss what these are doing at this stage. The BL command is known as branch and link. This is effectively a call to a subroutine. So this is calling the subroutine show hex, which happens to show R3 to the screen. And this subroutine is print string, which happens to show the string at address R3 to the screen. And we've got new line here, and monitor here, and memdump here. Now the one we're going to look at though is this infinite loop. Now this is a branch, not a branch and link. A branch and link is a call to a subroutine, like a go sub. A branch is like a go-to in BASIC. It just goes to a place. It doesn't ever expect to come back. So we're branching to something referred to as infloop. Now you'll notice that this is inset by one tab, but you'll notice that this line here is not inset by one tab, and it's got a colon at the end. Now this is what's known as a label. So this reference to branch to infloop is expected to be a label, and we've defined that label here. So this command here is jumping back to here infinitely. That's why it's called infinite loop. It's just it's effectively, it holds the processor, it stops forever. It's just a convenient way of getting the emulator to show the results of our program to the screen and not do anything anymore. So that's what we've got there. Now we've got other stuff here we're going to look in more detail later on. One final thing I will just very quickly discuss is the batch file that is doing the assembly work. So we are using the assembler EABI-AS here. That is that's the assembler toolkit. It's a free assembler. It's part of the GNU tools. So we're using that, and we've got all this garbage here. It's quite complicated, and we'll cover it in a Hello World series later on. But basically, we're assembling the file to an object file. We're then linking the file with this command here into an ELF file, an ELF file. But that isn't what our emulator actually wants. So we're using ELF to DOL here, and that is converting the ELF file into a DOL file. And then we are loading our emulator, which is G-Cube, and we are running our DOL file here. That is a binary file for this GameCube emulator. So I'm hoping you'll be able to just download the scripts and run them yourself. One thing I should point out with the examples here is I've tested all these examples with this emulator. There is a wide variety of GameCube emulators out there, and in my experience, if you download an open source game, it usually won't work on the emulator because the emulators all have different ranges of capabilities and limitations in how realistically they're emulating the underlying hardware, and you will often find that your free games and things won't work on the more advanced and more strict emulators. So all I am certifying at this point is that these examples work on the emulator I'm showing them, and I'm providing all of those examples and that emulator on my website. If you try and use these on the latest version of Dolphin, they probably will not work, and I can't guarantee that I will be able to make them work because of time constraints. I cover an awful lot of assembly languages in my tutorials. This isn't the primary one. This series is intended to teach you how to do basic assembly and get you started with the PowerPC. It's not intended to teach you to build professional GameCube games. It's designed for a bit of fun and a bit of learning only. So that is a limitation that I have to warn you of, just so you are not disappointed that you can't now sell your own GameCube games after watching this series. That's far outside of the scope of this. Okay, so what are we going to do in lesson 1? Well, every lesson has an assembly file, lesson1.asm. Again, download it from my website, build it yourself, and see these in action. Now, at the start, we have a branch command, and you will want to enable one of these branches by removing the comment mark. So I've removed the hash comma here from the immediate loads, and so when we run this now by pressing F6 and selecting EABIGC here and running that, now the emulator will start and we will get the result of this part of this program, and you can see it to the screen here. Okay, so this branch has jumped to this label immediate loads, and that label you can see just here, far left, colon at the end, that defines it as a label. These are tab indented, so these are defined as commands, and we've got a command li here. Now li stands for load immediate, that's what that stands for. Now we've got a register R0 followed by a comma followed by some kind of weird number here. Now the destination is on the left of the comma, the source is on the right of the comma. The value on the right, that is known as an immediate value. You can see it's coloured differently by the Notepad++, but it's the fact that it's a number it defines it as an immediate really in this case. So the li command loads the immediate on the right into the destination register on the left. So li r0, 0x1234 loads the value of 0x1234 into r0. Well, that's a bit weird, isn't it? I said that's a number, but it's got an x in it. Well, what does that mean? Well, the x within that number, the 0x at the start of that number, tells the assembler that this is a hexadecimal number. Now, hexadecimal is this weird thing that computers love to use. Now, many of you watching these tutorials probably actually know what a hexadecimal number is, but because I want to aim it for everyone, I don't want to assume that you've literally come across all of this stuff before. So we're just going to very quickly just demonstrate the fact that what hexadecimal is. So hexadecimal 1234 is decimal 4660, It also can be represented as something known as binary, which is just combinations of ones and zeros, or octal, which is not really used very often anymore. Hexadecimal digits can contain the value 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, 16 different options. It's far more convenient for converting binary and things like that. Now, I was using my own calculator program there, but you can actually use Windows Calc if you are struggling with hexadecimal and you need to understand it. So if you put calculator into programmer mode, you can click on the hexadecimal here and you can type in your 1, 2, 3, 4, and you can see it in decimal or octal or binary. That will work just fine. And you might need that later on when it comes to understanding why the source values you've put in haven't come out as you've expected. So I have got a tutorial specifically on hexadecimal. I'm not going to cover it much more here. I'm going to assume you're either going to look into it yourself or you already know it. You quite possibly, if you're looking at PowerPC assembly, you quite possibly already know it, but I don't want to just assume that. So anyway, so let's just fire up my program again, this example again, and let's see what we did. So we loaded the immediate value 1, 2, 3, 4 in hexadecimal, 0x means hexadecimal, into R0. And you can see when we've dumped our monitor to the screen, that's what this monitor function has done. It shows R0 contains the value 1, 2, 3, 4. These are being displayed in hexadecimal, so that matches. Our next line was loading R3 with 5, 6, 7, 8. And you can see that the register R3 here has been shown containing the value 5, 6, 7, 8. You will notice that these all contain 8 digits. These are 32-bit registers. And the values we loaded here are just 16 bits. And there's actually a good reason for that. And it comes to do with the way the commands actually assemble. Now, all of the resulting bytes from these commands, each of these commands will end up being 32 bits. And so half of those 32-bit commands are the value being loaded in. There will be times we want to load bigger values in, but we actually have to do other things to achieve that because the actual assembled code can't contain larger values, but we can get around that in various ways. So here we were running this monitor routine to show the result and then just starting a new line. Okay, now again, we've got a couple of warnings here. As I've already said, R0 is a little bit special. I've used it there, but it does have some limitations. R1, we definitely shouldn't do that kind of load to because we will end up crashing our system because the jump to the monitor routine won't work. But as I say, generally speaking, we're going to be using register R3 and onwards in our examples. Okay, so let's try some more loads then. There we were loading some hexadecimal values. Let's load something else. So here we loaded OX1234 into R0. This time we're going to load 1234 into R3. Okay, so let's have a look at R3 the next time we dumped our monitor to the screen. Well, R3 is here and it contains the value 4D2. Well, that's a little bit odd. What on earth is 4D2 about? Well, remember, it's being shown as hexadecimal. So if we do 4D2 in hexadecimal and then we click on decimal here, you'll see that's actually the value 1234. The point being that our value has been loaded incorrectly. So it's just been shown differently, but it is the same value 1234. So that is a decimal number. The difference is it doesn't contain 0x at the start. The prefix 0x defines the number of hexadecimal. No prefix defines it as decimal. Alternatively, and slightly strangely, and this again is a bit of a historical thing, if you put a 0 at the start of a number, so 0, 1, 2, 3, 4, well, that actually has the value 29c, which is a different value. And that's because a 0 at the start of a number defines it as something known as octal. This is a very old thing. It was more popular in the mainframe PDP 11 days, but most assemblers still support it. And so if you, for some reason, need it, putting a 0 at the start of your number when it doesn't need one will actually define it as octal. Alternatively, and far more usefully, if you want to work with binary, 0b followed by a series of numbers will define it as binary, and binary can only contain ones and zeros. Now, our value here of 4 ones in the low bits there, loaded into R5, is actually the value F in hexadecimal, or the value 15 in decimal. So those are various options for working with different types of number. We don't just need to deal with numbers though, we can also deal with letters. So basically here we are loading in ASCII values. We're loading in A, ASCII value A in quotes there, ASCII value B and ASCII value C here. And you can see those here in the values 41, 42 and 43. So if we need to work with letters to print them to the screen, for example, we can load them in like that. What about if we actually want to load in a very big number? Well, suppose we wanted to load in the value 1, 2, 3, 4, 5 in hexadecimal. Let's try that. Let's try loading that into R0 here. Okay, let's just fire it up. Well, where's our emulator? Well, it hasn't started. And if we look down at the bottom here to our debugging messages, it says error, operand out of range. And it tells us, well, that number is far too high. It won't actually load in. So we can't create a load immediate command with the value 1, 2, 3, 4, 5. Well, that's going to be a pain because we're going to have to work with very big numbers. We've got a 32-bit processor. We want to use 32-bit values. So how do we get a 32-bit value of our choosing into a register? We have to do it in two parts. We have a special command, not li. It's in fact lis, load immediate shifted. And shifted in this case means shifted to the top half of the register, shifted left by 16 bits. So we're going to load R3 with this value here, but it's not going to end up coming out quite as we expected. So we've loaded 1, 2, 3, 4 with lis into R3, and here's the result of that. The 1, 2, 3, 4 has been shifted into the top half of the register, the bit that we couldn't actually access before. Well, that's quite convenient because what we can do now is we can combine that load immediate shifted with a second command, in this case add immediate 5, 6, 7, 8. Now there's three parameters here with 2 commas. The one on the right is the one source parameter. The next one in the middle is the second source parameter, R3, and then the left parameter on the left of the 2 commas is the final destination. So this is saying R3 equals R3 plus 5, 6, 7, 8, and OX means in hexadecimal. So we've now added that immediate to the original value in R3. And you can see here that R3 used to contain 1, 2, 3, 4 in the top half, and now it contains 1, 2, 3, 4, 5, 6, 7, 8. And so even though we can't load that value of 1, 2, 3, 4, 5, 6, 7, 8 in one go, we can build it up into 2 parts. Well, that's quite nice, isn't it? That's quite handy for us. So that's how we get around the limitation of the maximum amount we can load. Okay, well now it's time to look at a new kind of way of working with numbers. What we're going to do here is we're going to have a value here. We've got this nice value here that we want to work with, but we don't want to refer to it as that number every time. We want to give it a name that we can remember. So we're going to call it testval, and we're going to use this equ command, which means something like equivalence or equals. And this is basically saying that testval is equal to the value fedcba98, and this is being done by the assembler. The assembler is remembering the word testval and this number here, and it's replacing every instance of testval with the value that we gave it here. So this is an assembler directive telling the assembler what to do. Okay, so now we can just use this word testval instead of that number. And what we want to do is we want to load that testval into a register. And so we want to basically do this in 2 parts like here. But we're going to have to basically split that testval into 2 parts, and the assembler is going to have to do that job for us. So how do we do that? Well, the assembler has some nice convenient ways that we can tell it to split that testval up into 2 parts. Now, what we are going to want to do is we're going to want to load an immediate shifted into our register, and then we're going to want add an immediate following on to that. And the way we do this is we use our testval and we put an @HA, the H being for the high part of testval and A being for addition. The second command we're going to do is going to use the low part of testval, so we use @L to do that. We're loading them into R3 and R4 here so that we can clearly see what happens. If we were actually going to use these properly, we would want to use LIS with the HA part, but we're loading it into the low part of R3 here just so we can see clearly what is actually going on. Okay, so our test value is FEDCBA98, and we're loading the high part into R3 and the low part into R4. Now you can see that the high part is being loaded with FEDD here, and the R4 is being loaded in with BA98. Well, that seems a little bit weird. Why has it been loaded in with FEDD and not FEDC? Because we wanted FEDC, and it comes to do with the fact that these commands are working with signed numbers, and signed numbers are a little bit weird in assembly. And so basically to get the correct value for R5, if we're going to use an add-I command, we actually in this case need to adjust it for the sign. And that's what that @HA does. So here we've done that, and what we're going to do here is we're actually going to use these two in combination, the HA, at HA and the at L, to load the true value of test val into R5. And you can see here that that is exactly what we've done. We've loaded the test val FEDCBA98 into R5 FEDCBA98. It has been loaded incorrectly by the combination of these two commands, and at HA and at L. So that is how we can load the two in with the combination of LIS and add I. However, there is another alternative way we can combine those two. We can use LIS, but instead of using add I, we can use OR I. Now, OR I is a logical operation. It's a bit complex. We're not going to discuss it at this point. But basically, that can also be used to combine the two halves into R5 of our test val. However, this time we're not using an addition command. So rather than using at HA for addition, we're just using the H command here, which is not for addition because we're not using addition, we're using OR I. And so this time you can see R3 was loaded with FEDC, not FEDD, which is the true top half of the 32-bit value here. And because we're not using addition, we're using OR here, so we're just using the at H and the at L there, but the end result is exactly the same. We ended up with the value that we expected. So there we go. You don't really need to worry about this too much. I'm just breaking it down into quite a lot of detail here. But basically, for loading a 32-bit value, you'll want to use LIS followed by add I, and you will want to use at HA to get the high part for the LIS command, and at L for the low part. And we'll see that later on. So there we go. So that's how we can load some immediate values. Let's see a few more simple mathematical commands then. Now that we know how to load values, let's try a few other things. Okay, so we know how to load our values here, and what we've done here is we've loaded the immediate 1000 in hexadecimal into R3. You can see that just here. Well, what about if we want to do some stuff with that value in R3? We want to move it somewhere else into another register, for example. Well, MR will do that, move register. So again, the value on the right of the comma, R3, is the source. The destination on the left, R4 and R5, are the destinations. And you can see that these commands have operated. Originally, R4 and R5 had weird values there that we don't really care about. But after those MR commands, they also contain the 1000 from R3. Very nice. So that's what MR does, moves a register from one to another. Of course, the source register is not changed. The term move is maybe a little bit misleading. It's more of a copy. It transfers the value. The original register is unchanged. Okay, well, let's try some more commands. Well, what about addition? We can add in an immediate. So we've got our value R3, which contains the value 100 here. And we're going to add the immediate value 22 to R3 and store the result in R4. And here we're going to add 22 to the value in R3 and store the result in R5. And so both R4 and R5 equals 122 here because of this. And the point I'm making there is that R3, the first of the two parameters, is unchanged. So R4 equals R3 plus 22 in hexadecimal, but R3 was never changed by these commands. It was left unchanged. Okay, so there we go. So now we know how we can do some simple addition with the add immediate command. Okay, let's try some more commands. Let's load R0 with the value 1000 in hexadecimal. Let's also load R3 with the value 1000 in hexadecimal. Let's try doing some add immediates. So we're going to add 22 in hexadecimal to R0 and 22 in hexadecimal into R3. And let's see what those two registers contain. Okay, well, R3, because it contained the value 1000 before, and we added 22 to it, contains 1022. Well, that makes a lot of sense. Well, what about that R0 register? What does that contain? Well, it only contains 22. Where on earth has that 1000 gone? We loaded it with a value of 1000, and we added 22, but that original 1000 just seems to have been lost by the add I command. The add I command treats R0 as a hardwired 0. I did mention this before. R0 has the special purpose of hardwired 0 in some cases. What cases? Well, it depends on the command. So the first rule of thumb is don't use R0, but the other thing is you need to check out the documentation. You can either get the official IBM documentation, it's free, it's linked on my website and it's very good, or you can get my cheat sheet, which is also free and is also hopefully very good. If we go to my books page here, we can actually see the documentation. And if we have a look at the PowerPC page, this is actually the old version. It's a bit embarrassing. This is an old version. I will get a new version uploaded. The new version does actually have a column that marks which commands treat the R0 as a hardwired 0. I will get that updated because that's the old version before I wrote these tutorials and updated it with that information. Anyway, if you download the latest version of the cheat sheet, which will be online by the time you see these tutorials, there is a column with the hardwired 0 marked on there, so you can see which commands actually will treat R0 differently. But as I say, the general rule of thumb is don't use R0 for anything, and what they recommend it for with the official documentation is doing things like pushing registers onto the stack at the start of subroutines and nothing else. I know you don't know what that means. We will cover that in a later tutorial as well, so don't worry about that. Well, why is R0 being treated as a hardwired 0 in some cases? Well, it's for convenience of the instruction set. We're on a RISC system here. This is a limited instruction set, and so certain permutations and combinations have to be used to do certain jobs. And so one weird thing is that the command that we've been using so far, li, is not actually a command. It doesn't actually exist in the instruction set. It's actually a pseudo operation, and the assembler is converting that to a command that does the job we need. And the command that it's almost certainly converting it to is an add I command, adding the immediate value we wanted to the R0, which is a hardwired 0, and storing the result in the register that we specified. And it's because R0 acts as a hardwired 0 for certain commands that the assembler is able to produce those results that we need. Okay, anyway, we've learned how to add immediates, but obviously we want to add registers as well. And quite simply, there is a command called add to do that. So again, it takes two parameters. The destination is on the left and the other two parameters are the source. So this is equivalent to R5 equals R3 plus R4 there. That's what add I does. We also have an add I shifted, which again works with the high parts. Not necessarily so sure you're going to need that, but it's certainly available to you. Anyway, you can see here that we did R5 equals R3 plus R4. R5 contains the value 1012 because R3 contains 1000 and R4 contained 12. Add I shifted here, well, you can see here that we've now added 333 to the top half of the registers. Again, shifted means shifted to the top 16 bits. Okay. Now, of course, we can specify a register as being both the source and the destination here. So here we are setting R3 to R3 plus R5. Here we're setting R4 to R4 plus R5 here. That will, of course, work just fine. And you can see that we've indeed done that just here. So we can use the same register as both the source and the destination in these operations. Now, what we're going to do next is we're going to look at some subtraction. And subtraction gets a little bit weird on the PowerPC, and that's because of the way that the actual processor deals with subtraction. The true subtraction command is called SuperH, which means subtract from. Now this, when we use these three parameters here, this means R3 equals R3 minus R5. R5 is subtracted from the third parameter R3 here, and the second one is R4 equals R3 with R5 subtracted from it. So the second parameter is subtracted from the third parameter and stored in the destination on the left there. So that's the true command, but we have a subcommand which possibly works a little bit more logically. And so this command here, this is actually a pseudo operation again, and this will say R3 equals R3 minus R5. R4 equals R4 minus R5, which is the way my brain would think about it, but they're actually converting it, the assembler's actually converting it to subtract from command, and it's basically swapping these two parameters around. The R3 and the R5 are the opposite way around with the subtract from command. But you can see, even though subtract from is maybe a little bit out of order to what we expect, it will work just fine. So here we've got our subtraction of 3 here, and you can see here we've gone down from 1,4 to 1,11 here after we've subtracted 3. and then we've subtracted another 3 here, and you can see that's gone from 1, 1 to 0e, and that is correct. These are hexadecimal numbers here, so maybe the numbers don't quite look as you would expect, but those are the correct subtractions there. As well as subtracting from registers, we can also sort of subtract immediates. So here we're going to subtract hexadecimal 10 from R5 here and store the result in R5. I say sort of because actually this command doesn't really exist. There is no subtract I command. It's a pseudo operation again. What actually happens is we're adding an immediate value of -10 in hexadecimal. Again, not particularly relevant what we really do. You just need to know that it does indeed work. And so that's what's happened here. We've subtracted our 10 there, and we've also subtracted 10 there. And you can see the numbers have gone a bit weird with lots of F's appearing. That's just the hexadecimal representation of negative numbers. Again, if you need to understand that, I've got a tutorial series that covers that. So please see that tutorial series if you need to understand hexadecimal numbers better. Now, again, I'm talking technically when I'm referring to the fact that sub-I doesn't actually exist. For practical purposes, it doesn't really matter what is an actual command and what is a pseudo operation. When I'm programming, I will usually just consider the two to be the same thing. I have had the occasional commenter comment that you're saying this is a command, it's not. So I do try and mention what is a pseudo operation and what is a true command, where I even know the difference, but it doesn't matter for you as a programmer as long as your assembler understands how to assemble them. Okay, now the last thing we're going to discuss, it's a little bit complicated, but we're having to use branches to subroutines as part of our examples because we keep calling these monitor routines to show the results to the screen. So we're just going to very quickly discuss branches. Okay, so first of all, we've got this branch and link, and that's a call to a subroutine. And what we're doing here is we're calling this print char routine, which happens to show register R3 as a character to the screen. So we are going to show the letter A to the screen here. We're then going to show the letter B to the screen, and BL branches to this subroutine. It means branch and link. Now, don't worry about what link means. We'll discuss that in a second. So you can see A and B on the screen here because of these two calls to that subroutine, branch and link. Remember, a go sub in BASIC is the same as a call, same as a branch and link. So that's what's happening there. We've then got a branch to this skip C command. Now, this skip C is a label. Where is it? Well, you can see it just down here. So what we've actually done here is we've got this code here which would show the letter C to the screen, but it never happens because we've branched straight over it. A branch, just like a goto, it's a one-time jump, there's no return. So that's what we've done there. Now, what we're going to do next is we're going to use the branch and link, which is our call, like our go sub, and we're going to jump to a subroutine called print D. Well, we've got a label here called print D, so this is our subroutine. Now, there is a problem here, and that is with regards to the way that the actual processor deals with subroutines. Some processors like the Z80, they push the return address onto the stack and pop it back off when you return. It's a very easy way of doing things, but it's not necessarily the fastest if you're not going to nest your subroutines, and so the PowerPC does things differently. It's got a special register known as LR, the link register. And when we do a branch and link, what that link part means is it means load the link register with the return address. And when we do our BLR, that means branch to link register, and that's effectively a return. What this does is it sets the next running code to the address in the link register, and that means that the link register must contain the address that it did when we use the branch and link command here. Otherwise, we're not going to return there. And the reason that might not contain that is if we use a subroutine, because this branch and link command here sets the return address for this position, but we're then running a subroutine here, which will also set that same branch and link register. So now the original value has been lost. Well, in this case, the simple solution is we're going to move from the link register, MFLR, into R4. And then we're going to move back to the link register from R4 here. And I know that this print char routine doesn't use R4, so R4 will be unchanged by that subroutine. And we've now preserved our link register in that way. Now, there are alternative ways of doing this. We will look at the stack later on and we'll see how we can use the stack to back up our linked registers. But that's outside of the scope of today's lesson. We've already covered an awful lot of stuff, and I think a lot of people will be probably struggling a little bit. So we will go into lesson 2 and we will cover more stuff, including that kind of thing. Okay, so we've branched to subroutine print D here, and subroutine print D simply prints a D to the screen, not very complex. We run it a second time there just to prove that it is indeed a subroutine, and then we show an E to the screen here, and that's what you've got here. A, B, D, D, E. The D subroutine was called twice, and the C was not shown by this print char routine here because we branched over it with this branch command here. So that's how we can have branches in our code and how we can call subroutines. And we've been calling subroutines all the way through this. Every time we've shown the contents of our registers, we've used a branch and link, a call to a subroutine. We've got a branch to an infinite loop here, which is just the end of our code. And at the very start of our code, we had branches to the various subsections of this tutorial. So as I say, I would have preferred to cover that kind of thing in a later lesson, but we just had to do it because of the way these tutorials work. Anyway, I hope you've enjoyed what you've seen today. If you have, please like and subscribe. There's a whole following series on the PowerPC coming. I've also got one coming on the SuperH, the SH2. I've also got them on all of the other major processors that are out there. Z80, 6502, 68000, RISC-V, ARM, Thumb, you name it, I've covered it. All of the major ones I've already covered. So if you thought this was interesting but you want to do something a bit more mainstream, a bit of Z80 maybe, please take a look at my YouTube channel, my website, and of course get that cheat sheet. It's free, so you would be stupid not to. Thanks for watching today, and goodbye.